and Radu for the invitation to give a talk at FFT seminar. I mean, now I think it's called Faraway Fourier Talks. I remember this was called February Fourier Talks, then Fall Fourier Talks, now Faraway Fourier Talks. But I really enjoy that you are keeping up, especially during this time. I mean, this idea of talks. So let's see, I'll be talking about Parseval wavelet frames on Riemannian manifolds, and this is the abstract of my talk. So the idea is that I would like to construct Parseval wavelet frames in L2 of M on a general Riemannian manifold, and I will try to explain how this can be done. I will also not only talk about Hilbert space, but also LP spaces, so show existence of wavelet unconditional frames in LP. And all of this is possible thanks to some kind of construction that I don't think it was present before. We call it smooth orthogonal projection decomposition of the identity operator, which is like an operator version of smooth partition of unity. And once we do this, then I'll show you some applications, characterization of Triebel-Lizorkin spaces, Besov spaces on compact manifolds in terms of magnitudes of coefficients of Parseval wavelet frames. And this talk is based on a joint work with Dziedziul and Kamont. So let me tell you what will be the plan. So the plan, I will probably spend half of the talk talking about this concept of smooth orthogonal decomposition of identity in L2 of M. So there will be several parts like Hessen's operators that probably you don't know what these are because this is not well known. Then we'll talk about smooth projections on the real line, Morse functions. I mean, they don't really belong to analysis, but because it's more algebraic topology or differential geometry, but nevertheless, we'll have to use them. Latitudinal projections, lifting of H operators from level submanifold, and finally, we'll talk about the smooth decomposition of identity in LP. Once we have this done, then finally I can explain how we construct those Parseval wavelets, and I will give you the applications. Okay, so that's the plan. So now let's get going. So what is the setting? So in our setting, we assume that we are given a smooth, let's say connected Riemannian manifold, for simplicity without boundary. And Riemannian manifold means that we have a metric G that defines an inner product. So we have inner product at any point of our manifold. And this inner product, I mean, from the viewpoint of analyst, I mean, what is needed for at least from my viewpoint, it's needed, it's useful because it defines measure. When you have an abstract manifold, there is really no, I mean, you cannot really talk about natural measure, but once you have Riemannian manifold, you will have a natural Riemannian measure. So every metric induces a Riemannian measure, and I wrote just the formula defining this Riemannian measure. So when you have a chart defined on an open subset of manifold, and you have a function that's defined on that manifold, you want to compute what is the, I can probably use the pointer. Let's see if this will work. Let's see if this will work that way. Yes, so you want to define what is the integral of that function with respect to that Riemannian measure. What you do, you need to bring back to the setting of RD. There is this determinant of that metric, because this metric is symmetric bilinear form, so you can compute this determinant. You take square root and multiply by f. It's like a weight, and then of course you integrate this, and you first have to show that this somehow, when you have two local charts, this definition coincides, and but then but this is like a change of variable factor here, and then you can use partition of unity and let's say Riesz representation theorem to show the existence of Riemannian measure. So that's from the viewpoint of analysis, that's what we need. We need a measure to work, because once we have measure, we have integrals. So like for any p between 1 and infinity, I can talk about LP space of Lebesgue space of respect to that Riemannian measure. And of course, the most interesting case is when p equals 2, we have a Hilbert space with the usual product. I didn't put here, but maybe I can take advantage of that. If the functions are complex valued, then you need to put complex conjugate. Right, so that's the setting. I mean, Riemannian manifold with Riemannian measure. And now let's talk about this result about smooth orthogonal decomposition of identities. 2021, it's appeared, but we had this result years earlier. So suppose you have a smooth Riemannian manifold, again, for simplicity without boundary, and suppose you have any open and pre-compact cover of that manifold. Right? So just family of open sets, they are pre-compact, so their closure is compact. So then there is this wishful list of 5 things that we will have. So associated with any element of the cover, I will have an operator PU. And this operator PU is going to be orthogonal projection, right? So it's on L2 of M. And those orthogonal projections, when you add up over your cover, they will add up to identity operator. Because they are orthogonal, I mean, their composition of any 2 projections will have to be 0. But on top of this, you have other property. They preserve infinity function. So when you take infinity function and you project it, you get again infinity function actually with compact support. But what is even more important for that is that those projections PU, they are localized on those open sets CU. So what does it mean localized? I mean that when you take any function f, when you project it, you get again function that will be, but the support of this function will be inside U, right? So I mean somehow this projection maps into functions that will be supported on that set U of the cover. But moreover, there's some other property. If you start from a function that doesn't have any, its support has empty intersection with U, then projection is equal to 0. So somehow that's what we mean by localized. And then this family, moreover, is locally finite because, well, you can ask what if this is infinite sum, in what sense does it converge? What does it mean? For any compact set of the manifold, only finite for all but finitely many open sets U that intersect non-trivially K, P of U equals 0. So somehow P of U has to be equal to 0 for pretty much all of those, except finitely many. So that there is really no problem about interpreting this convergence of that series. Right, so hopefully this looks new to you, at least maybe, yeah, we couldn't find this result in the literature, but it's very close to something that should be familiar with you if you have taken differential geometry, and this is called smooth partition of unity. It's a very basic concept. What is a smooth partition of unity? It's a family of functions, PU, that's always somehow, yeah, it's subordinate to the open cover again of a manifold. So those functions phi u are first of all sin infinity. The support of the function phi u is in U. They are non-negative and they add up to 1. And moreover, we have this finiteness condition that for every x in M, you can always find neighborhood small enough so that if the function, so that the supports of phi u intersect empty with that neighborhood for all by finitely many U. So if this family is infinite, then basically there is really no problem. I mean, only finitely many of those terms in that series are non-zero. Otherwise, yeah, if you're outside of that neighborhood, you'll get 0. So this is very close to what we had before because, okay, what we can do, you can talk about multiplication operators. Once you have the partition of unity, you can just have multiplication operator, you multiply by that function phi u from your partition of unity. So this will be localized in the sense that we talked about, and they will also satisfy this property that sum of PU will be identity because, yeah, this adapts the identity. However, there is one problem. So basically, when you come back to this previous slide, you can basically make all work, this work, property 5 work, property 4 work. They will be smooth because property 2 work, but well, you have already problem with those. But property 1, how do we make this to be orthogonal projection? That's the problem because this multiplication operator is orthogonal projection if and only if, I mean, the function phi u takes value 0 or 1. And that's a problem because, I mean, phi u would have to be discontinuous, right? I mean, so not even C infinity. So how do you, I mean, yeah, so that would be naive way to try to prove that theorem, but it will not work because you cannot just have multiplication operators. So you need to construct your operators from largest class of operators, which we call hastiness operators, that preserve all of these properties and additionally guarantee that P of U are orthogonal projections. So I have to modify this definition of P of U somehow to make it orthogonal projections, but also not destroy the previous properties that we had. Okay, so now Hestenes operators, what are those? I mean, Hestenes paper is from like 1940s. No one probably even knows, but this is not a new idea. So this comes from the paper of Ciesielski and Figiel. The title of this paper is Spline Bases in Classical Function Spaces on Compact C-infinity Manifolds. It's a paper from 1983. It's tour de force paper. I mean, it's very, probably ahead of the times what they did. I mean, constructing spline bases before wavelets on compact C-infinity manifolds. And over in this paper, they have this class of Hestenes operators. So how do they work? So suppose we have phi, capital Phi diffeomorphism between two open subsets of a manifold, V and V prime. It's in C-infinity. That's one thing. And then the other thing that you want to have a cutoff function. So it's a function on the manifold with real values, which is compactly supported, but its support has to be inside V, right? And now what is a simple H operator acting on a function? Basically what it does, it's like a change of variables. So there is a H of f of x. You precompose f with your diffeomorphism, but the problem is that it will not map C-infinity to C-infinity functions because how this, and outside of this is zero, right? I mean, that's what, but so you need to smooth things out, you have this function phi that's supported in V. So then when you multiply this by this change of variable, basically the composition by phi, you get a nice function. You get a function that will be against C-infinity. So, and what would be an H operator? Just a finite sum of those simple H operators, and that's how we denote the space of HM operators. Yeah, I could probably try to draw a picture for you, but I'm not sure if this would work. Yes, I mean I can probably try to draw it, but I mean something. Yeah, so we have this diffeomorphism phi, capital Phi from V into V prime, and then yeah, so we have a function. Maybe let me try to draw like this. So this would have a function f mapping to reals. So of course, what we have this precomposition phi composed with phi, f composed with phi. But the problem is that this function is, you want to make it globally. I mean, it's all living inside the manifold or some manifold M. So somehow to make it nice, you have to somehow. So there will be function, let's see, so except I probably missed, so P into V prime, exactly, so this, so the function F was on the manifold, so probably my picture was already not correct because I wanted to have, so let me just correct this a tiny bit, so that's supposed to be F composed with phi, here, right? Because that's so function f and let's see. So yeah, when you have a slides, it's okay. So so then and diffeomorphism will go from V to V prime. Okay, so that's okay. So no, this was probably okay. What I had before.
No. It is okay. The one you just erased was the correct one.
What was correct one exactly? Yeah. Because I'm trying to overdo things.
No. F composed phi from V into R.
Yes.
And
yes, exactly.
F from the manifold into R, and then.
Yes, exactly. That was.
So.
Thanks for thinking. So exactly. So my picture. I should probably draw a manifold M here. Okay, I'll be drawing some kind of nonsense, but maybe these people will try to think what I'm trying to explain. But then you multiply this by a bump function somehow, right? So that at the end you get a function. So you get somehow f composed with phi, but you multiply by this function phi, so that you get a nice, right? I mean, okay, so that's maybe the picture. But now this is an algebra. I mean, when you have this Hessian operators. When you compose them, you get again Hessian operator. You can also do tensoring, where one operator acts on manifold M, the other on M prime. You can, it somewhat determines operator on the product of those two manifolds, M and M prime. But what is also important is, because these are such simple operator, and if they're localized on open pre-compact sets, then they induce bounded operators basically in any function space that you can think of. So for example, continuous functions, continuously differentiable functions up to order R, this will be, they are bounded. They are bounded on Sobolev space, yeah, because that's again, the fact that we have this cutoff function that will help that. And then, well, if the manifold has bounded geometry, has complete Riemann manifold bounded geometry, you need this assumption of bounded geometry in River to talk about those Triebel-Lizorkin Besov spaces. You also have boundedness. These are not completely trivial results to prove those. So you have to work a little bit to prove it. But so I think those two basically belong to Dziedziul and Figel. Those, the other two, yeah, they were also noticed by Dziedziul and Figel in the compact case, but the bounded geometry, it's our result. Okay, so now let's get back to something more down to earth. I mean, something that maybe you have seen, maybe you haven't seen, and I'm not sure, maybe Victor is in the audience. So, I mean, well, this is, I want to define something called Auscher-Weiss-Wickerhauser operators, because this is the first paper where we found in 1992 where these operators were formally defined. But this comes back, I mean, I should probably add also names of Koopman and Meyer, because that's where this operators will appeared. But this is very simple type of operators that maybe you can teach even in your basic real analysis class, because what we do is the following. We start from a function that I'll try to draw the graph of this function, a cutoff function. Let's try to draw just the picture of this cutoff function, how it will look like. Yes, so that's how more or less it looks like. That's the graph of S, right? And this is, there may be like minus delta. So it's supported from minus delta to infinity. You have this symmetrical, this is equal to 1. What is the Auscher-Weiss-Wickerhauser operator? It looks like this. So you just multiply by this cutoff function. Well, there's also this parameter theta because you want to shift it. And then you have this reflection happening around theta. And this function is actually supported, has small support, because when you multiply S of t times S negative t, it's supported from minus delta to delta. So it's a very simple formula. It's just multiplication operator times some multiplication by reflection. This plus or minus is referred as the polarity of this operator. But okay, but this operator will be mapped infinity function to infinity function. But what is nice about this operator is actually its orthogonal projection. Yeah, so I don't know how many of you have seen this result, but it's, well, it's in the book by Hernandez-Weiss, so probably it's should be known. But essentially what we are doing is the following, is that when you have, I'll try to again draw a picture. When you have a theta here, what essentially, what this function, what it does, this operator, it just, it's almost like a projection. I mean, the non-smooth projection would be like, this is a non-smooth projection where you just multiply by a sharp cutoff function where you kill values of function which are less than theta and then preserve for when it's bigger than theta. But then you have to smooth out. So you smooth things out. Maybe let me try to smooth this out. I mean, so essentially, it's essentially multiplication by that function, except there is something going on maybe in that interval. Let me just show you this interval from minus ups. Something happened. You see, this is not. This tells me that I probably have to go faster. Okay, something is happening here between theta minus delta and theta and delta. I mean, it's not just multiplication, but okay. But this is a well-known result. So look up this paper and Hernandez-Weiss book, and you will find it. So now Morse functions. So what is a Morse function? So it's a function defined on a manifold, so that at every critical point, the Hessian matrix has rank D. So critical points mean just that the gradient is equal to 0, and the Hessian matrix means that you take just d by d matrix of second derivatives. That's the Hessian. So this is some review of properties of the Morse function. If you have a connected Riemannian manifold without boundary, it doesn't have to be compact or not compact. You can always find a Morse function that looks like this. The primitives of those interval from 0 to b's are always compact. In particular, the level sets are compact, but every critical value corresponds to exactly one critical point. And moreover, this maps, if manifold is not compact, it maps onto 0 to infinity, or 0 to 1 if the manifold is compact. So it's basically like one parametrization of your manifold by a function, by a real valued function. It's used in algebraic topology to classify manifolds and stuff like this. So now I would like to define what are those latitudinal projections. I can call this like AWW operators on manifold. So once you have your Morse function and you have theta regular value of m, you can find interval that doesn't contain critical values. And then what you will be doing, you want to define this orthogonal projection. There exists this orthogonal projection that will preserve your function at heights bigger than theta. So let's say theta plus delta. Delta is this slight error. Below theta, so theta minus delta is 0. And then in between, there will be this Hestenes operator that we talked about. Right, so that's what we will do. And now you can partition, when you have partition of the interval from 0 to infinity into intervals that contain only regular points, you can define those latitudinal projections, which are just projection onto this projection above theta I and this projection above theta I minus 1. So you get projection into that strips that are, you get smooth decomposition of identity, which is subordinate to the open cover into that strips. And maybe because I like pictures more than just this, let me show you the picture of how the latitudinal projections look like, because it's just the sphere. What will be the Morse function? I'll try to draw Morse function like this. So Morse function will be, so at the South Pole it's 0, it's equal to 1 at the North Pole, right? And then when you, let's see if I'll try to destroy this picture. So this may be theta I plus 1. This is theta I. So what you have like a projection. So you have this projection that I denoted by Q theta I plus 1, or maybe I had a different order, Q theta I plus 1. So this is the projection on that band, on the latitudes that lie between this latitude theta I and latitude theta I plus 1. It's not a sharp projection, so there is a little bit of a fuzziness happening on the edges because you want to have this smooth, right? It's not just a bilingual function of this, yeah, and this is, and then you can decompose into those strips. You basically cut. You imagine that you slice your manifold by knife into those strips, into those latitudes, and you can have, if you use a sharp knife, you have those projections will be non-smooth. But if you use like a dull knife, those Hestenes operators, you can make those smooth. You can make this to be smooth projections. Okay, so now let's continue with this. So once you could smooth this out, then you can. There is something called regular interval lemma for Morse functions, if you know what that is. But if you have Morse function that doesn't take any, takes only regular values on some interval, let's say from theta 1 to theta 2, but actually you want to enlarge this interval, so it takes regular values on this enlarged interval. When you take any open cover of the level submanifold, so J theta, so this level submanifold will be here. Let me try to show you pictorially. That will be, I'll try to draw it. So my picture is probably not that great, but the level submanifold in this picture, this is J theta. This is just, yeah, this is the same as the sphere, S1, right? I mean, so suppose you have open cover, but of that level submanifold, and you have smooth orthogonal projections of that level submanifold with respect to the Riemannian measure, but on that submanifold, then you can leave this, you can find a smooth projection of this latitudinal projection that I have drawn before, but subordinate to that open cover. So somehow you can lift those projections that live on that level submanifold to the whole manifold. Well, but they will be orthogonal, it will be like the composition of that strip, just that strip that you have here. So what you get, I mean, you get again this picture that maybe I'll draw this level submanifold here. Of course, destroy this picture, but that's probably okay. I mean, this goes like you have this J theta, but then you somehow leave this, and you started, by the way, from orthogonal projection on one. So you had like here you had projection into those intervals, which on the level submanifold, and then you somehow leave this to. In fact, I was not drawing this properly. I should be drawing this here over the. Somehow you leave to the projections and then give those patches, and that's basically how you imagine the smooth orthogonal projection will look like on the sphere. Okay, so I think that's how much I wanted to tell you about this, except maybe you can do the same for LP space, right? It's the same. So once you have pre-compact open cover Riemannian manifold, you can find this locally finite family of operators which are localized on each element of the open cover. These are projections. Orthogonal 1 equals 2. Yeah, when you compose two of this, you get 0. They add up to identity, convergences in unconditional instruct operator topology. But then instead of, you don't have equality as equal to, but you have some kind, those projections, when you compute their LP norms, they add up to LP norm. So yeah, you can do this also in LP if you really want to, but it's a lot of work, but okay, it can be done. Okay, so now let's talk about wavelets. I mean, it's already we are halfway through. So I would like to talk about wavelets on manifolds and give you some historical background, because some of the people are actually in the audience who are, okay, so Ciesielski-Figel, this paper from 1983, where he constructed a spline based on compact manifolds, was the first one, in my opinion, in this area. I mean, before wavelets even existed, but before wavelets were constructed using splines. Then there is this paper of Dahmen and Schneider. They were probably one of the few who really understood what Ciesielski-Figel did. They constructed wavelet bases on compact manifolds using their approach. They use this for some other things, like, and then there is a paper of Geller-Mayerli, I think it's sort of independent, 2009, where they constructed nearly Parseval frames on compact Riemannian manifolds, but they used some kind of Laplace-Beltrami operator, and were only able to get nearly Parseval frames. There's a paper of Goller-Pessenson where they constructed 2011 Parseval frames on compact homogeneous spaces. There's also papers by Coulon, Karkachirian, Petrushev on band-limited frames on complete Riemannian manifolds with Ricci curvature bounded from below and satisfying some volume doubling property. And 2013 paper of Pessenson on, again, nearly Parseval frames on non-compact symmetric spaces, and probably there could be some other work. But our goal was basically to what? Eliminate compactness assumption that was prevalent in previous assumptions, or maybe this Ricci curvature assumption, and construct this tight Parseval wavelet frames. And this is possible thanks to that result that we talked about. And what is the theorem? I mean, this is the main theorem. Well, no, first, before I give you the main theorem, I need to talk about local Parseval wavelet frames on RD. They are just on that cube, minus 1 to the power 1D. So what I'm claiming that you can always find for every m smoothness and every epsilon, you can find a set of functions. They are indexed by jk. This is j is basically dielet. K's position is this index that, because we need to have to the power d minus 1 wavelets. So j scale k. Technically, I'm cheating here because somehow, let me maybe make this correction, because yeah, so a is not, let me just make sure that it's work. So let's see, so e is not equal to 0 if j is positive. So it's like a non-homogeneous family, yeah, so you have basically to the minus, so it's to the power minus d1 wavelets, because that's how many you need when you use dyadic wavelets. Okay, so what do they satisfy? They will be they will be smooth, they will be supported now in this enlarged cube, but then you have this reconstruction formula that works fine when functions f which are supporting q. Then you get Parseval. So they're like a local Parseval frame. They are not Parseval frame on the whole space L2 of Rd, but they are local on the L2 of q. And how to get those? So you can construct a orthogonal projection such that H is Hessen's operator. It will map infinity to infinity, and what it will do, it will when you are in the cube, it doesn't do anything to your function. The values get the same. Outside of that cube, you get 0, and you can get this by somehow tensoring this construction of Osher-Weiss-Wageker-Hauser operators. It's not too difficult to construct. And then what you do, you start from the usual d-dimensional Mayer wavelet that consists of to the power d minus y wavelets, and you apply this Hessen's operator. So somehow you cut off them away from that cube. And you get a local Parseval frame from that. So once you have this local Parseval frame, this is the main result. Parseval wavelet frames in L2 of M. So M is the smoothness parameter. It could be equal to infinity. So what we do is that, we have a family of functions. So this f, e, j, k, these were local Parseval wavelets living on Rd. Then there will be this transfer operator that I will explain, T2 of x, and this is P omega of x. This is this smooth orthogonal decomposition of identity. They will be indexed by x, some discrete subset of M. Omega x is the geodesic ball of radius r. Radius will depend on x. So for every point around that geodesic ball, you will somehow transfer your local Parseval wave frame for Rd using this change of variable operator T2 of x. So what is that? So I already explained what is omega of x. This is geodesic ball. We have that cover. This is a cover of the manifold, so we can use our result and find smooth orthogonal decomposition of identity. But then you want to transfer those functions FEG. So this is isometric isomorphism that takes you from the ball. It's not uniball, 3 times root of d is the dimension, but ball in Rd to a geodesic ball on the manifold. And it's basically you have this exponential geodesic map that appears here. There is this denominator, you have weight to make it really an isometry, but that's what you do. And then you combine this with P omega of x, and somehow, so you transfer this first wavelets from, they somehow they lift on that ball in Euclidean space, that transfer them to geodesic ball. And then once they live on the geodesic ball, you hit them with those orthogonal projections. And then what we claim that this family W2M is a Parseval frame in L2 of M that consists of CM functions localized on geodesic balls. And yeah, this is the Parseval identity that you have here. Okay, so that's the main result. Maybe I can, the proof of this, I mean, I don't want to maybe say, I mean, just, it's a bit tedious, but I mean, you can sort of see what you can do. Once you have those orthogonal projections, this family T2 of x, they sort of, I mean, this will be like a Parseval from the subspace obtained on the range of that projection, and then you glue them together because you have using this result about smooth decomposition of identity. And
Marcin, can I ask you something? In the previous slide, when you have the local Parseval frame, so this is so really the I mean, they're all, it's like inside it. If you were inside each cube at a certain scale, you have, I mean, they're all supporting so they haven't moved here. It's all happening in. Yes,
exactly. Yes, they haven't moved. So imagine that the easier way to understand this is maybe the Dobeschi wavelets, that somehow you can, when M is finite, you can use Dobeschi wavelets, and basically you just take wavelets. I mean, I'll try to draw the picture, even though I probably fail, but I mean, if this is my cube, there will be actually two cubes. There will be this cube Q epsilon, and there will be this smaller cube Q. in it. And then basically you take the Bsp wavelets that, and there are dyadic intervals. I mean, so you will be taking only the ones who are basically, they never, so they'll be supported on those cubes, and maybe they have to touch it. I mean, because you want to have, but they'll be somehow supported inside, right? I mean, so you take, and these are the dyadic cubes that I call, I don't know, maybe QJK. I just probably it's okay. I mean, QJK, dyadic cubes, right? So, and basically the Bsp wavelets are supported not at the dyadic cube, but maybe a little bit a bigger cube than that. So, but if you scale properly or take those to be fine enough, you'll taking those dyadic cubes, or taking the Bsp wavelets whose support will intersect Q, but because of this, they will only, the scale is large enough. I mean, they will be lying inside this Q epsilon. But with Meyer wavelets, it's a slightly different story because you have to somehow cut off them. I mean, so they are like the Meyer wavelet maybe support is over there, but you cut off, you still get some kind of remnant here, right? So that's why they are fully indexed by.
Maybe so who is Q? Is Q the unit cube?
The Q is the unit cube. Q is here. Yeah, Q is the cube from -1 to 1 to the power d.
Okay, so the Q epsilon is a little bit enlarged. I got it now. Thank you.
Yes, enlarged. And basically, you can think of this like the Bsp wavelets. When the scale J is very large, then they will have small support.
I know the problem. It's -1 minus epsilon, 1 plus epsilon to the d. That's why I'm so confused.
Yes, exactly. This is one. Yeah.
Okay.
Yeah, but it's a larger.
Yeah, there we go. Now I get it.
Yes,
thank you.
Yes, exactly. That's why probably it's good to ask questions so that but this is, and then you can do this with Meyer wavelets, because the normal Meyer wavelet will be, if you take it will be living somewhere, it will be also associated with some dyadic cube QJK, but will be living there, but it has infinite decay, so, but it will feel, it will leave some kind of small trace on that cube, but this trace of, I mean, you apply this Hessen's operator somehow, because there's underlying Hessen's operator that somehow, it's a cutoff function. So so you have to localize this because you want to localize your functions to that cube Q epsilon so that you can use that change of local chart like this geodesic map to map it into manifold, right? I mean, that's because there will be your manifold. I can probably destroy this picture, but it's okay. I mean, there is your manifold M, right? And there is this locally you have this charts that will be denoted. Maybe it's even exponential maps that X exactly that, and or maybe inverse of that, because that's actually exponential map goes the other way around from X into, right? And then you want to transfer those wavelets by on RD to living on the manifold. That's what essentially this operators T2 of X do this, and you have this normalization. Okay, so you have Parseval wavelets in L2 of M, then you have Parseval wavelets on LP. You can also do that. It's not a problem. I mean, because we have this smooth orthogonal decomposition identity can be expanded to LP spaces, except you have to change TP of X, this change of variable. There is a parameter P that depends on P. So, but the manifold doesn't have to be connected. It doesn't have to be bounded. You still have this dual wavelet system. And then finally, applications. Once you have this, you can decompose function spaces. So for this, we'll assume that it's, let's say, compact space. And once you have compact Riemannian manifold, you have this smooth decomposition of identity, which is subordinated to that. And Fm could be any function space on which Hessen's operators are bounded. And we already know they're bounded on CR of M, I mean, continuously differentiable functions with continuous derivative up to order R, or Sobolev space, or Triebel-Lizorkin space, or Besov space. We know we have the composition of this function space into direct sum of subspaces. And moreover, the norm of your function is like comparable to the sum of those components, because this sum is actually finite. Yeah, because this is a projection. So this is just that's how you define the subspace. I mean, if you use the smooth partition of unity, this wouldn't be a subspace. That's the advantage of having projections, that this defines subspaces. And those subspaces consist of all functions that are supported inside you. That's why it's like localized decomposition of the function spaces that you get using this smooth orthogonal decomposition of identity. And now, because of this, we have application to function spaces. We have wavelet characterization of, let's say, LP spaces. M doesn't have to be necessarily compact. When M is compact, you can characterize Sobolev spaces, Triebel-Lizorkin spaces, and Besov spaces. So yeah, so LP, yeah. So if the space is not compact, we can do LP, but that's how much we can do. We need to assume compactness, and that will be one of the problems that I will pose at the end. I mean, how far we can go beyond compact case. Okay, so more specifically, what we'll have. So this is a bit dense slide, but what does mean characterization of by wavelet coefficients? You need to describe the sequence space of wavelet coefficients, and I would like to talk about Discrettive-Lizorkin space. That was, I think, this notation was probably introduced by Fraser and Jaworth. I mean, this small f SPQ. But now we have this also on manifold. So suppose we have manifold, it has to have bounded geometry, because otherwise you cannot talk about even Triebel-Lizorkin spaces outside of that class of Riemann manifolds with bounded geometry. Suppose you have this W2M, a Parseval frame that consists of CM functions which are localized on those geodesic balls. Because we have bounded geometry, this radius stays the same for all ball. Then suppose S is the smoothness, P is integrability, Q summability index in the Triebel-Lizorkin space. So what is that? This is the sequence of set of sequences that are indexed by elements of your Parseval wavelet frame. So this is the same Parseval frame that we had, but with that strange norm. Well, this is this Q, like a square function, but it's Q function. There are characteristic function of omega jk. You should think of this as a dyadic interval, but it's not exactly that. I mean, you can see it's a dyadic interval. There's some scaling going on. You have to use this the inverse of the exponential, this geodesic exponential map. This is essentially dyadic cube, because it looks like dyadic cube here, right? I mean, but except you somehow periodize this. It's a bit more complicated than that, because if your cube is outside of the ball, then you bring back to the ball, because this K prime, so K minus K prime has to be here in this. So it's like you take a representative of ZD, so that you land back in that cube, so that you can take the, so this X map will be actually well defined. You have to somehow bring back. It's like periodize. If the other cube is far away, then you put it back into that ball, and that's the part. And then you just compute this Q norm, and then once you do this, you compute LP norm of that. So for those of you who have seen this space FSPQ on RD, that should be familiar. This is, I mean, that was, except here there is this issue about this yeah, that you have to be careful what happens with that. You somehow periodize those dyadic cubes. So what I'm saying is that maybe here, if the dyadic cube lies far from that cube, maybe somewhere over here, then you need to bring it back here. I mean, so you keep the cubes that are somehow inside in that ball, but then if they're far away, then you somehow bring them back so that this will be well defined. Okay, so what is the result? So suppose we have compact dimensional manifold. We have this Parseval wavelet system of smoothing parameter M. M has to be large enough. I mean, this depends on this parameters P and Q and the dimension. That's M has to be smooth. Your Parseval has to be bigger than the smoothness of your Triebel-Lizorkin space, and also this sigma PQ minus S and minus S. Okay, so now if you have any element in Triebel-Lizorkin space, this could be also LP. I mean, because this is maybe I should probably say this for those of you who are not familiar with this, that this space F0 P2, that's just LP, at least when P is bigger than 1. And when P is less than 1, you have Hardy space. When S is positive, then you have Sobolev space. And so this is like a unifying class of function spaces. So when you look at its wavelet coefficients with respect to the Parseval wavelet W2M, you get a sequence, and the Triebel-Lizorkin norm of that sequence is equal actually to the Triebel-Lizorkin norm of F. So we have equivalence of norm. And the convergence, well, moreover, when you synthesize, you take those coefficients with respect to the wavelet system multiplied by your wavelet. you get back F. With unconditional convergence in the Triebel-Lizorkin space, I guess we need to reduce smoothness if equals infinity. So this improved the results of Triebel by allowing M equal infinity. So he had similar result, but when M is finite, because he transferred double shear wavelets. Now we can transfer also Mayer wavelets, but also he had also dual frames, and now we have Parseval frame because we have the smooth decomposition of identity. So this is almost characterization of that. There is a warning that I wanted to give you, and this is probably the last important slide, that this wavelet system that we have, W2M, which is defined by localized Mayer wavelets, is highly redundant. So to guarantee that synthesis operator is bounded, so the synthesis operator that I wrote with this definition of FSM that was like here is actually not bounded, because you need to add this additional decay factor. You need to somehow impose that when you are outside, for indices which are outside of that that cube, you have additional decay. They have additional decay, those coefficients. First of all, you have to show that for this operator that's you have this additional decay, and then for synthesis, when you put this and you impose this additional decay, then the synthesis will be actually bounded. So this is the in reality the characterization by of the Triebel-Lizorkin space by discrete by wavelet coefficient. So this is, there is this extra term. For the previous result, you don't need this because the previous term I don't really talk much about synthesis. I synthesize with respect to the Parseval coefficients, but if you synthesize with respect to some other coefficients, Sp, which are random, you need to have that. Yeah, the time is almost over. So open problem. So the open problem is I would like to extend this wavelet characterization of Triebel-Lizorkin spaces from the case of compact manifolds to manifolds with bounded geometry. But for this, I don't know. I mean, we are not experts in Morse theory. I mean, you have to construct like a Morse functions that will give you better projections that will be uniformly bounded on Triebel-Lizorkin space. I have no idea how this is, how to do this, how to, I mean, we were just barely able to work with Morse functions, and we had to reprove some kind of results about this. And but people who know better differential geometry than we do, maybe this is doable. And then because you have the system W2M that we had before, I mean, it exists on any compact manifold. I mean, any manifold that's not necessarily compact. So you can ask questions for non-compact manifolds, and that becomes much harder. Okay, so I think I will finish. So thanks a lot for your attention. I'll be happy to answer any questions you have.
Thank you, Marcin. Thank you for a great and exciting talk. Ladies and gentlemen, please unmute yourself, and if you have any more questions for Professor Bownik.
If I understood, your frame elements are all compactly supported, is that correct?
Yes, they are all compactly supported, exactly. They are supported on the, let me come back to the slide that talks about...
Yes, yes, understood, right. So it means that band limitness in any sense doesn't enter your construction, right?
No, it doesn't. They're just compactly supported on the geodesic bonds.
How do you construct discretization? Usually it is connected with certain notion of band limitness.
Yes, exactly. So what I do, I mean, this is this idea of this local Parseval wavelets that Christina asked the question about. I mean, that somehow, once I know, have wavelets living on the cube, like -1D, which is an RD, then I can just, it's a very basic idea. By diffeomorphism, this exponential, this so this exponential geodesic map, I just transfer those wavelets living on the balls, and then I glue them together, right? I mean, we glue them together using this P omega of X, which is this those projections that map.
Yeah, and that relates to my question, because I assume that you're taking advantage of the Koifman-Mayer construction, which allows folding of basis elements on the ramping region. Like, you can sort of picture this as a sine on the left, a cosine on the right, making them really skinny, putting a bump function, which is it could be ck for any k by creating B-spline bumps, or, you know, e to the -1 over x squared, so you can have a C infinity map. And that's the advantage of that construction, is that you are able in that little region to fold basis elements so that in the global picture it looks seamless. And I would assume that that's the point of the construction.
Exactly. That's how we do this in manifolds. So for those who have seen Kaufman-Meyer construction, that's why we call this Osher-Weiss-Dickerhauser, because we couldn't find paper of Kaufman-Meyer where they really define explicitly, I mean, implicitly there. But but that's how they construct wavelets. Wavelets on the real line. I mean, this is the first chapter of Hernandez-Weiss. You can,
Yeah. And so I'm also friends with engineers, and so maybe the name Enrique Malvar, you can add that to that list of people who, and he did these basis, folding basis results in the engineering literature. So
exactly. So Kaufman-Meyer and then and Malvar, yes.
Yeah, exactly. Oh, okay. No, correct.
Yes.
Thank you very much. It was very, very enlightening.
Can I ask you something, Marcin? So when you're defining the Triebel-Lizorkin, the Besov spaces on the manifold, so you went to the sequence spaces, but you had the definition. Didn't the definition also depended on your basis elements?
No, the definition is dependent. So let's see when I
it doesn't matter which basis element you're choosing. You're landing in the
Yes,
thank you.
Exactly. So let me just try to find this descriptive. So I should probably put a slide. This is actually work of Triebel, but once once manifold has bounded geometry, but this is important. Basically, what you do, I mean, maybe I'll use because I have a little probably. Right, you can define the space.
I see you have the characteristic functions in there. No?
Right, exactly. But you define this by just what you do. You have this. Okay, you have partition of unity by geodesic balls, and you somehow. So what you do is basically you look at F composed with x minus. And then this will be the Triebel-Lizorkin space that will work on the RD. And there is also cutoff function here that I have to put also like alpha j cutoff function. So you have, and of course, so what we start from is that you alpha j, you have partition of unity. Like respect to some geodesic balls, but they have to be geodesic balls, and then you have this is like infinite sum, something like that. That's how you can more or less show that you have Triebel-Lizorkin space, and this definition doesn't depend on the choice of the partition of unity. Yeah, but this is, yeah.
Yeah, thank you. How did this compare to the O'Shea-Hitone wavelets?
But they exactly. It's a very nice construction because this is O'Shea-Hitone. They have, first of all, they have much general space of homogeneous type. But yeah, this is, I mean, it's probably, I don't think it's a different construction. Yeah, I mean, they also construct nice, I think maybe even orthogonal.
Splines. It's a splines, but they are not compactly supported. So it would be really nice if one could do, well, I mean, maybe in the last 3 years they managed to build it, but as far as I knew, they were not compactly supported. So if one could merge these two things.
Exactly. So if you could somehow generalize, so here we definitely in our menu. So the question basically comes back to this result about smooth decomposition of maybe this in LP, but it's when can you construct those projections that we localized on each, and then you could probably but I don't know what this is. We need smoothness. We can probably do this on manifolds of smoothness C1, and if you wish, but it will be smoothness.
Well, I mean, even continuity he has, but compact support, that's what they were lacking.
Yes, the compact support.
And you do have compact support. So even if you don't have, you just Helder smooth or whatever you can define in a general space of homogeneous type, may be interesting.
Yes, yeah. So maybe that's another open problem, open direction for people to study. I mean, how to, except here we use Morse function and of course we use this idea of cutting your manifold into those slices, right? I mean, it's a completely different approach. And once you have the slice, then by induction, you just keep doing that. So it's a different,
Well, in the space of homogeneous type, what you're using dyadic grids, right? That
Dyadic
you do
grids.
have that. They do it so somehow. Yeah. Thank you.
Ladies and gentlemen, any other questions?
I had written a trivial question in the chat regarding definition of local finiteness.
Local finiteness. Okay, so let's see. So there is a local.
You say PU is 0, you say, but
Okay.
actually you want that U intersection K is not empty for all but finitely many.
Yes, yes, for all but finitely many U that are not that have non-empty intersection with a compact set K, you want the operator P of U to be 0.
Yes,
right?
but PU 0, you don't want PU 0 because you only took non-zero PUs. So you only want that only finitely many U's should intersect K.
Yeah, no, you see, that's the issue. You may start from a cover that will have the property that infinitely many U will intersect K, non-trivially, compact set K. But only finitely many of them will, but then you have operator P of U corresponding to all of those, but then it will be a 0 operator, actually. Yeah, so that's that local.
So you are not wanting to include 0 operators as such. The operator is not wanted to be 0, only finitely many U's are wanted to intersect K.
Right, only finitely many you get like you can non-zero contribution. Otherwise, this is like it doesn't appear. You can just throw away elements from that open cover and have like a smaller cover that will be locally finite. That's the other way to explain this. You start from a cover which is not locally finite. You can find subcover, just fewer elements that will be locally finite. That will be locally finite. You satisfy all of this property.
Yes, agreed. But you are not wanting PUs to be 0. PUs are non-zero projection.
Yeah, exactly. So PU is a 0 projection. This 0 means that it's a 0 projection. Yes. Yes.
Marcin, we also have a couple of questions in the chat.
Okay,
if you could open it.
Yes, at one point
Great talk. Great talk.
Yes, I can.
Very good talk.
Okay, thanks. Let me just.
So there was a question about whether the measure gives you the metric
at
the very beginning.
Probably not. At least I think for any measure that's. I think the measure is somehow. What you have, there could be probably. My understanding is that there could be many metrics that give you the same measure. Somehow that the measure will not be. If I'm not, but I'm not. This, yeah, you see, this. I feel like a student, and you are asking some basic question, differential geometry, which I don't know. From the top of my head, from once you have a measure, it has to first of all has to be like a smooth. I don't think the metric will be determined. There could be many. Given the same measure, you can have. There could be different metrics that give you the same measure, but that's. And to go the other way around, from measure to get a Riemannian, I don't know. Probably not.
Yeah, so I was the one who asked the question. I wondered if there were some special test functions you can use to get back, but that's okay if you're not familiar with that.
Yes, I don't know. For me, this is, I need just that Riemannian metrics to have a measure, and then I don't care about. So technically, if it's a random manifold, then the problem is that I don't have a measure. There's like a d-dimensional volume form, but it's not a measure. So does the measure give you the metric? I think it should give you a metric, but it's not unique. That would be my answer.
Okay, yeah. And then question is what the equivalence relation is. Okay, thank you.
Yes, I don't. That should be known, I guess, but I don't even know where to look at.
Thank you.
Well, if there are no more questions, Marcin, thank you so much for a very insightful talk and detailed answers to our audience. That was really great. Thank you very much.
Okay, yes, it was nice. Thanks a lot.
Thank you everyone for